Hi everyone! In this video, we're going to explore one of the most fascinating and fast-growing fields in technology, quantum computing. Don't worry if you're not a physicist. We'll walk you through everything step by step, and by the end, you'll see how you can start experimenting with quantum algorithms right from your laptop. Quantum computing is one of the most interesting and increasingly popular topics of the last few years, as continuous research breakthroughs are pushing the boundaries of what we believe possible and of what we know about the quantum world. The field is blooming, and software developers can start learning more about it today. Even if that seems impossible at first glance, this video will show you that there's no need for a quantum physics background to start playing with quantum computing and writing simple quantum algorithms. In particular, we'll use Python and Qiskit, IBM's quantum software suite, to solve the problem of generating a truly random number. This problem already showcases something that classical computers cannot solve. As a matter of fact, in classical computers, random numbers are not truly random, as they're usually taken from a sequence generated from a seed. Knowing the seed will let us predict all the numbers in that sequence. Quantum computers, on the contrary, can leverage the laws of quantum mechanics to generate truly random numbers. By putting a qubit in a superposition state, a state that is a combination of the 0 and 1 states, and then measuring it, the outcome is fundamentally probabilistic. This process is the source of our true randomness. Let's dive into how to solve the random numbers generation problem using a language like Python that leverages a quantum computing simulation library. We are going to use Visual Studio Code IDE with Python and Jupyter Notebook support. Let's start by creating a new Jupyter Notebook. Then we'll set up a virtual environment to install the dependencies we need, in particular the following packages. Once the installation is complete, we'll be ready to move on. Next, let's define our algorithm to generate a positive random number, less than or equal to a maximum value. We'll start by determining how many bits we need to represent the max. Then, using a quantum circuit, we'll generate as many bits as needed, concatenating them to form a binary number. We'll turn it into a decimal one, returning it if and only if it is less than or equal to max. The first step is to build a quantum circuit, which is a sequence of operations, also called gates, applied to one or more qubits. In Qiskit, we create a circuit by specifying how many qubits and classical bits we need, respectively the first and second parameter, to the quantum circuit constructor. Then, we apply a Hadamard gate to the only qubit in the circuit, and we measure it. Drawing the circuit will show the gate applied to the qubit, effectively putting it into superposition and the measurement operation. We can now simulate the circuit, running the quantum program a fixed number of times. For this, we'll use Qiskit's Air Simulator and wrap the quantum circuit inside a function. Then, we run the circuit, specifying the number of runs as a parameter. Furthermore, we use the memory parameter to tell Qiskit to record and return the measurement outcomes for each shot of the simulation. Lastly, we collect those outcomes and print them. Running the code multiple times will return different measurements. For example, 4 distinct outcomes in the case of a 4-bit number. We can now extend our function to use the simulation result to build a binary number. To do so, we'll use Python's join and int functions to join the content of the measurement array into a string and then turn it into a number. We print the result for logging purposes. Again, each time we run the function, we generate a new number, which could possibly be greater than our max. A different solution would be creating a circuit with as many qubits as needed to represent the maximum value, rather than using a single qubit and simulating the circuit multiple times. This way, we would only need a single simulation, but the algorithm would possibly need a very large number of qubits, which might be not practical or feasible on real quantum computers. Lastly, let's implement the comparison logic. First, we determine how many bits we need to represent our maximum number. A neat way to do this in Python is to use the bit length function. Then, we create a loop that repeatedly builds and runs our quantum circuits until the generated number is less than or equal to max. Running the function might show in the logs that a few numbers were generated and discarded before one that satisfied our constraint was found and returned. Did we get you curious about quantum computing? If so, head to our technical note to read more on the topic, including a comparison of different quantum simulators. Also, make sure to watch a conference talk recently delivered by one of our engineers and start experimenting with your qubits today. Thanks for watching.